Last but not least, we have Spurthi here to talk for us today. Spurthi is an engineering student at Stevens Institute of Technology and is interested in LLMs, generative AI, and their applications towards finance. Today, Spurthi will be covering parameter-efficient fine-tuning, LoRa, CLoRa, reinforcement learning with human feedback, prompt engineering, and FLAIR. Let's all welcome to the stage, Spurthi. Ready whenever you are, Spurthi.
Thanks, Christy, for that introduction. Hi, everyone. Today, my talk is going to be more about the technical side of how we actually go into fine-tuning these large language models. So picking up for where Catherine left off of why exactly we should go about this process. So I'm sure a lot of you are familiar with the Gen AI models that are already on the market, like ChatGPT. They kind of are really good at more like general tasks. It's pretty cool. You can have a conversation with a computer, but they kind of fall short when you want them to perform really well on a specific use case. And that's where fine-tuning comes in. If we want these sorts of models to have very consistent outputs based on these use cases. So kind of on the image on the right, you could see that during the pre-training process, a large language model is just fed in a large corpus of text data, but not really given specific instructions. So it's just statistically predicting what's the most next likely word or token. And maybe through its text data, that data, when you ask it, hi, what is your first name? It thinks the most likely response is, what is your last name? But that doesn't really make sense when you're like talking to a person. So maybe after you fine tune it for a chat bot specific application, after when you ask it, like, hi, what is your first name? It knows to respond with something, my first name is blank. And going into more of the benefits of fine tuning, it's also really good for reducing hallucination because now the model won't necessarily have to make up that it knows this information when it doesn't, because you'll be given it domain specific data set throughout the fine tuning process. And it allows us to kind of get similar results for of a model performing good for a specific use case without having to train a model completely from scratch, which is a very computationally expensive process. And this is going more into the architecture of how fine-tuning actually happens. So as I mentioned, first, the large language model goes through this process called pre-training, where it is fed a huge amount of unstructured text data. So you can think, for example, GPT was basically trained on the entire internet. And the large language model here is not really given any sort of instructions. This is really familiar with the format of the language, and it's trying to teach it how to speak coherently in a sense, but it doesn't have specific knowledge or trained to do anything in a certain way. And after we have this pre-trained large language model who just kind of has no knowledge, but how to speak in a way that makes sense, we can then go through the fine-tuning process via a very domain-specific data set. And this domain-specific data set is generally a lot smaller, higher quality, and more specialized than maybe the massive data set, which is usually just a large corpus of unstructured data. So once we go through the fine-tuning process, which I'll talk more about, we're going to end up with this fine-tuned large language model that'll have higher quality outputs for a specific case that the user can directly interact with via queries. Now, these are the three main fine-tuning methods, and they're kind of similar to traditional machine learning methods. So first is like self-supervised learning, which you can kind of thing to unsupervised learning. And in this type of fine-tuning, we don't have structured data in terms of inputs and outputs. It's actually going to be more so like unstructured data, but that can be very domain specific unstructured data. So for example, if you're trying to like legal or like a financial chatbot, maybe you'll just feed in additional documents of like, of the cases or like finance documents just for the model to get more familiar with the language. But then again, you're not specifying it like, oh, for this input, it should be this output. That's where supervised fine-tuning comes in. And that's what I'm going to mostly talk about during this presentation. And that's where you have paired inputs and outputs, which kind of correspond to the input being, the user's query plus any additional context or input, and the output being what the expected model response should be. And then you can improve it further through reinforcement learning. And this is kind of like in addition to like even after you fine tune, the model's kind of actively learning via human feedback. Now, for supervised fine tuning specifically, there's a very specific data creation process to go through. And Catherine mentioned the four models we fine tune. You know, the closed LLMs being GPT and Claude, but open source ones being like GPT for all and Llama 2. But each large language model requires it to be in a very specific format to fine tune it. That you can find it in its docs or information about that large language model. Usually, it'll be in some sort of like JSON or JSON-L format where you have to specify maybe the role of what the model should be, and then also maybe specific tags that tell the model to perform in a certain way. And like any other machine learning model, high quality data is essential if you want high quality performance. Because when you fine tune, the whole goal is to get more consistent outputs to be like the fine tuning data. If you want your model to have a high performance, you need to have high quality data. And the pre-processing techniques is very similar to maybe other natural language processing tasks where you need to tokenize them, which is basically chunking the data into smaller sections like a word or two, and then creating embeddings, which are just numerical representations of the text. And we can also incorporate prompt engineering via the dataset creation for the fine tuning, where maybe we can concatenate the inputs in a specific way that's saying, you are a financial chatbot that acts in this way, use this input, this is your question, use this input to answer the questions. And that would kind of all be incorporated in the training data for fine tuning. Now, this is going more in specific about how we fine tune via a process called parameter fine tuning. So you've probably kind of heard people talking about these things called parameters when talking about large language model, GPT being something like 175 billion parameter model. And generally is the more parameters it is, the more complex and the higher performing model it'll be. So because these large language models are so complex, they often have billions of parameters. And when you fine tune it, you're actually updating and changing those parameters and the weights of those parameters to make it optimal for that specific use case. And there's three kind of buckets that this method falls into. So you can do full fine tuning, which is basically like we take all the parameters, all the weights of like the base LLM, how many ever billion of them, and through the fine tuning process, you update every single one. And that could lead to really good results, but as you can imagine, it'll be extremely computationally expensive because you're updating billions of parameters and runs the risk of maybe the original model will have some catastrophic forgetting. Now you can get better than that through something called transfer learning, where you're not updating every single model weight, but you're freezing all the parameters except the model head. And the model head is something, it's basically the last layer of the neural network that translates directly to the output layer. So you can kind of think of that one as the most important one. And we're only going to update the parameters for that one. But we can get even better than this through a process called parameter efficient fine tuning, PEFT, where actually in the base pre-trained LLM, we're going to fix all those weights and augment additional weights. And only those augmented weights are what we're going to change and update via the fine tuning process. And as you can imagine, since we're not updating any of the original weights, it's a lot less computationally expensive to do so, but you can kind of achieve very similar results. And this is kind of a graphic to explain that further. So on the left, you can see in conventional fine tuning, all the original model parameters are updated, which can be pretty expensive. However, on the right with PEFT, we can augment additional weights and then only fine tune those, which is significantly less computationally expensive. Now, kind of going further in how we can further optimize the fine-tuning process is through a process called low-rank adaptation, or LoRa, which is something that some researchers at Microsoft came out with a few years ago, and it's kind of been widely adapted across the community. And this is a way that from PEFT, we can further reduce how many parameters we need to train through the use of low-rank matrices. So basically what that means, if you kind of take an example, right, of like weights are stored in these matrices, and if you have like a 10 by 10 matrix, you would need to update all like 100 weights in those. But LoRa reduces how many you need to update through storing them in a low rank matrix. So, and the product of them. So instead of a 10 by 10 matrix, you'll have the product of a 10 by 1 matrix and a 1 by 10 matrix, and that one kind of being a rank, which is a very low number. Now, instead of updating 100 weights, you only need to update 20. And that's kind of a very small number, but you can imagine when it scales to thousands or like billions of parameters, it could save you a lot of time. And it also reduces the risk of overfitting because you're updating less weights and via these low rank matrices and only updating the most crucial ones. And as you can imagine, because we're significantly reducing the number of weights and parameters we have to update, it is even less computationally expensive, and you need significantly less memory requirements as well as the GPU required to do this process. Now, we can get even better than LoRa through something called QLoRa, which is basically it's doing the same thing that LoRa does, but for a quantized large language model. So quantized LLMs just mean a large language model that has gone through the process of quantization, which just means that for each of those tensors in the model, we're going to reduce the precision to make it a lot more compact. So usually these methods will reduce something like a 16-bit number to a 4-bit precision number. You can kind of like, see the analogy of like on this image, if it's to 2 decimal places, it'll reduce the precision to just like an integer. And maybe it'll make the model a little less, accurate, but it'll make it a lot more compact. So it takes up significantly less memory. And you can do LoRa on that to get very comparable results. And this has further really democratized the process of fine tuning as reducing the, computational requirements, that is, to make the process a lot more accessible. And kind of going more into uh, the research we did and how we fine tune and the results from that. So we took Llama 2, which is an open source model. We specifically fine tuned the 7 billion parameter one. And originally, with just a simple RAG pipeline without fine tuning, our model was not able to perform very well. When asked a question, it did not find the answer in the given text. But after we fine tune it, this is specifically with the finance bench data, it was able to come to the correct answer. And I also want to talk about the aspect of retrieval for fine tuning, because we're specifically working on document-based question answering, right? So a lot of the times the model itself won't have all the knowledge, but it'll have to get it from additional sources. And this is a graphic here that kind of explains how a traditional RAG pipeline works. So RAG stands for Retrieval Augmented Generation. So the user may ask a question. Using that question, it'll retrieve the most relevant docs, and then it'll kind of give those docs into the base model for it to generate a response. But there's kind of a more issues with this when you go into like more complicated, like for example, financial documents, where maybe something that is the most similar is not exactly the most relevant. So we also looked into ways, how can we actually improve the retrieval? Because what's the point in having this model that's really good at answering questions based off of a given context if you're not able to give it the correct context in the first part? So one way to do that is through query expansion, and we did a method of this in our research called FLAIR, forward-looking active retrieval. Maybe you ask the LLM for a hypothetical answer, and then use both of those to find the relevant chunks. You can also employ prompt engineering in terms of like how it retrieves the context and uses the context in the answer. After it's retrieved the chunks and, maybe they're kind of rank them initially based on like cosine similarity, but maybe that's not actually where the answer is. You can employ a re-ranking algorithm that sorts it more based on relevance rather than just similarity. You can play around with the chunking parameters, how big each section you want it to be, and maybe more dynamic so that each chunk is not the same size. And we all can also do things like metadata filtering, where we annotate each chunk with additional data that maybe of like the time, if you only want to get the most recent results, or like if it's like a larger data set, things like, company, topic, other informations to really get a more advanced retrieval architecture. And in order to build really robust and high quality AI systems, it's not really one or the other. You'll sometimes hear people say, oh, should you use prompt engineering or RAG or fine tuning? But really, you can use all these methods in conjunction with each other, and you should be using them all together in order to get the best results. And I'm kind of going into how we can do this. So as I explained with the fine tuning process, we actually do use RAG and prompt engineering. When I create my data set, I'm actually creating a prompt template that, for example, that says you are a financial chatbot that can only answer questions based on the given context, like do not hallucinate information, which prevents it from making up information. And that's a version of prompt engineering. And we also use RAG as like the fine-tuning data has, in addition to the query, it has an input of the context of where the information is located, because we want it to improve the retrieval too. And even after we fine-tune and got that optimal fine-tuned model, we should still be employing these techniques of like asking prompt engineering, maybe asking it a way that's similar to the training data, so you can get the outputs that you expect. And we should actively be using RAG so our model can constantly be up to date with the information it should answer questions off of. And as kind of a future step, we can also implement other things like reinforcement learning to further improve the performance. And these are kind of just next steps of how we want to further improve our models, like, in the fine tuning process and like past it at ANO. So one way is via hyperparameter tuning. So this is kind of different than updating the model parameters. That's actually changing like the weights. Hyperparameter tuning involves things like maybe you want to change like the chunk size of the retrieval, or you want to change the learning rate when you're actually fine tuning the model, or like number of epochs, like the things like those sort of hyperparameters. Maybe we can play around with and see what's the optimal one. We really wanted to see if we can incorporate more active learning via reinforcement learning through actually having a reward algorithm that responds to human feedback, in addition to just doing supervised fine tuning via a human curated data set. And I did talk about those I kind of touched upon a lot of the methods to enhance retrieval, but we implemented something called Flare, but we're also definitely want to kind of implement and look into the performance of some of those other methods I had mentioned to see how we can really ensure that we're getting the most relevant and correct context that gets the answer. And finally, a lot of the methods I mentioned, like, PEF, LoRa, and QLoRa, a lot of great research and work has been done to make these fine-tuning a lot more efficient and accessible, but there's still room to do a lot more, right? Like, even when you fine-tune, even when you're doing things like LoRa and QLoRa, you need a good amount of GPUs to like get it really efficient. So we're like looking for like things of how can we get it, both model inference and the fine-tuning training process, to be even more efficient and faster. And with that, I think that kind of concludes my talk about more of the technical side of fine-tuning LLMs. Thank you.